Viewers, in this video we'll see the hop subtractor, the construction of hop subtractor using the NAND gate. By using the NAND gate, how to construct the hop subtractor. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Before going to the NAND gate logic, we'll see what is the hop subtractor. Then we'll go for the construction of hop subtractor using NAND gate. So hop subtractor is a combinational circuit that subtract 2 bits and produce the difference, right? So hop subtractor will perform subtraction of 2 bits. Full subtractor will perform 3 bits. It also has an output to specify if a 1 has been borrowed, right? So it will give the details about the borrow also, whether the 1 is borrowed from the previous digit, right? So there are 2 inputs and 2 outputs, 2 inputs AB and 2 outputs, difference and borrow. Let us designate the minuend bit as A and subtrahend bit as B. The result of operation A minus B, all possible values are tabulated below, right? So we will see the truth table of the hop subtractor. So there are 2 inputs A and B. Because of 2 inputs, there are 4 possibilities are available: 0, 0, 0, 1, 1, 0, 1, 1, right? So this thing we already discussed how to perform this 4 operation. So the output is available. Output is the difference and borrow. 0 minus 0 is very simple. Difference is also, there is no borrow. Then third one, we will see the second one last. 1 minus 0. From 1, if we subtract 0, again it is difference is 1. There is no borrow. 1 minus 1. From 1, 1 is subtracted means difference is 0, borrow also 0. Right. So for the first combination, third and fourth is very simple. There is no borrow. 0 minus 0 is 0. 1 minus 0 is 1. 1 minus 1 is 0. For the third one, the second one, 0 minus 1. The first number is smaller and second number is bigger. We already discussed that. We have to subtract 0 minus 1. We have to perform the subtraction. So in this case, we need to borrow 1 from the previous digit. So at that time, what will happen? It become 10, right? Now 10 minus 1 is 1. How it is? 10 is nothing but binary equivalent of the decimal equivalent of 2. So 2 minus 1 is 1, right? So borrow is 1. We borrow 1 from the previous digit. The difference is also 1, right? So I will explain again. 0 minus 1. The first number is smaller and second number is bigger, so it is not possible to perform the subtraction. We need to borrow the 1 from the previous digit. While borrow 1, this 0 become 1 0. 1 0 is nothing but decimal equivalent of 2. So 2 minus 1 is 1. So the difference is 1 and borrow also 1. The difference is 1 and borrow also 1, right? So this is the truth table of the hop subtractor. Now you need to develop the logical expression for difference and borrow either by using the K-map or directly from the tabular column also we can develop. So there are 2 1s are available here for a difference. The second term is 1 and third term is 1. First and fourth is 0. What is the second term? 0 1. 0 1 means A bar B. This is A bar B. The third term is 1 0. 1 0 means A B bar. A B bar. Right. So A B bar plus A bar B. There are 2 terms available. So A B bar plus A bar B is nothing but A XOR B, XOR gate, XOR operation. Right. Similarly, the borrow only 1 1 is available. What is there? 0 1. 0 means A bar B. A bar B is the borrow. Right. The expression for borrow. Right. So that same thing can be implemented with the K-map also. There are 2 inputs A, B. A available vertically, B available horizontally. Right. So there are 2 1s are there. 0 1 is 1. 0 1 is 1. 1 0 is 1. Right. So this cell is 0 0. 0 0 is 0. 0 1 is 1. 1 0 also 1. 1 1. The fourth cell is 1 1. 1 1 also 0. Only these 2 1s are available. So these 2 ones are available individually, not possible to combine. We have to write the terms individually. So while referring this, we need to refer the second row and first column. Second row is A. the first column is B 0, so that B bar. So A B bar, A B bar. While referring this, you have to refer the first row. First row is 0, 0 means A bar. Second column is 1, 1 means B, right? A B bar plus A bar B. By using K map also we can give. Similarly for the borrow, two inputs A B, two combinations 0 1 0 1. So only one, this is 1, that is 0 1 is the 1, 0 1 is the 1, 0 0 1 0 1 1 is 0 only this one is available. So what is available correspondingly here? 0, 0 means A bar. What is available here? 1, 1 means B, A bar B, right? From tabular column we can write it directly, otherwise by using K map also we can write. So we got the expression for borrow and difference. Borrow is A bar B. Difference is XOR gate of A and B, A XOR of B. Now we need to implement these two expressions using the logic gates in order to get the borrow and difference output. Now we'll go to the logical implementation. So this is the two inputs A and B is available. What is borrow? Borrow is A bar B, right? So A is available, that is connected with one NOT gate, so that it become A bar, that is given to one AND gate, because A into B we need one AND gate, and this B is given directly. So B and A bar is given, so that it will give A bar B, borrow. A bar B we need one AND gate, one input is B, another input is A bar. A is available, by using the NOT gate, A bar is given. What is the difference? Difference is nothing but XOR gate. Simply by using XOR gate with input A and B is given directly, we got A B bar plus A bar B, right? So this XOR gate will produce the output of difference. This AND gate will produce the output of borrow. So that we got the half subtractor, we got borrow and difference by using this logical circuit, right? Here we have AND gate, here we have XOR gate. Now we will see some of the limitations of the half subtractor. In multi-digit subtraction, we have to subtract the 2 bits along with the borrow. So while subtracting, the borrow is available. So definitely we need to take the account of borrow, right? So 2 bits along with the borrow is the practically available subtractor. Only 2 bit is not available practically. Practically it is impossible, right? So effectively such subtraction require subtraction of 3 bits, right? So it is not, so this is not a possible with half subtractor. Half subtractor gives only 2 bits. Practically what we need? 2 bits along with the borrow. So that is the, there is a limitation of the half subtractor. But the half subtractor, by using half subtractor we can construct the full subtractors. So that still we are using the half subtractor also, because half subtractor using we can construct the full subtractors, right? So in this video we discuss about the half subtractor. What is the truth table? What is the logical expression? That logical expression is implemented with the logic gates. The one limitation is practically we need 3 bit, that is 2 input and 1 borrow. But in half subtractor we have only 2 bits, that is the limitation. So, but still we are using the half subtractor, because half subtractor can be used to construct the full subtractors, right? Subscribe this channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. We will see how to implement this half subtractor using the NAND gate. First we will see the expression for difference and borrow. We already got the expression for difference and borrow. The difference is nothing but A B bar plus A bar B, that is XOR gate. The borrow is A bar B, right? So this A bar B, A B bar plus A bar B. But while using the NAND gate, what is a NAND gate? Is nothing but that is AND gate. AND gate with inversion. AND gate means multiplication. So the A into B is possible. A into B bar is possible. A bar plus B is possible. A bar B also possible. These both are multiplication. But here one addition is available. So by using the NAND gate, we cannot go for the addition. So we will convert into everything into multiplication, so that we can easily implement with the NAND gate. NAND gate is multiplication. A into B into C, like that. So that this subtraction, this addition is available, that is OR operation. In order to implement with the NAND gate, this plus is converted into multiplication, so that we can easily implement with NAND gate. So for that, what we are doing, we are taking the complement 2 times, so that the original value will not affect. A B bar plus A bar B complement of 2 times, right? How to simplify this? By using the De Morgan's theorem, A plus B the whole bar equal to A bar plus B bar. A bar into B bar. A plus B the whole bar is nothing but A bar dot B bar. The plus is converted into dot by using the De Morgan's theorem. A plus B the whole bar equal to A bar into B bar. Similarly, we take this is A, this is B. A plus B the whole bar is A bar into B bar. So based on that, A B bar is as a taken as A, so that A B bar the whole bar dot A bar B the whole bar. Again, one more complement is available. So we have taken the De Morgan theorem applied for only one complement, another complement available as it is. So by applying this De Morgan's theorem, A plus B the whole bar equal to A bar into B bar, this plus symbol is now converted into multiplication. See this, now all are multiplication only. A into B bar, A bar into B. Again these two are multiplied, so that can be easily implemented with the NAND gate. All are AND operation. There is no OR operation. This OR operation is now converted into AND operation, so that we can easily implement with the NAND gate. This borrow already available only with the AND operation. Now we'll go for the implementation of this logical expression. So the two inputs A and B is available. This is the A, right? This one is B. In order to get A bar and B bar, we are using one NAND gate with the same input. Two inputs are shorted together, only one input is given. If the NAND gate with only one input means it will act as a NOT gate, NOT operation. So A means it will give A bar. Similarly, here we are using one more NAND gate with the same input. Both the inputs are shorted, only one input is given, so it will act as a NOT gate. So B means it will give B bar. So now we have all 4 inputs are available. A bar, B bar. All 4 inputs are available. We can use these 4 inputs for the logic circuit, right? So for implementing this, here we need one NAND gate. Here we need one NAND gate. In order to multiply these two, again we need one more NAND gate, right? So this is the 2 NAND gates are available. For further operation, one more NAND gate, right? What is the input to the first NAND gate? A B bar, right? So the A is connected and B bar is connected, so that it will give A B bar the whole bar, because NAND gate will give A B bar the whole bar. AND gate means A into B. NAND gate means A into B the whole bar, complement, right? So A into B bar the whole bar, that is the output of this NAND gate. The second term is A bar B. So the A bar is connected and B is connected. So the output is A bar B the whole bar, because of NAND gate. This symbol indicate it is the NAND gate, right? NAND operation means complement. Now these two terms are available. A B bar the whole bar, A bar B the whole bar. Now these two are given to one more NAND gate, so that we will get another one more complement. So that is our final requirement. We need one more complement, that is A B bar the whole bar dot A bar B the whole bar, again one more bar, because of this NAND gate, right? Now we'll got the final expression for difference, right? For this we are using one NAND gate. For this term we are using one NAND gate. For multiplying these two, we are using one more NAND gate, right? What is the difference? The expression for difference, A bar B the double bar, right? A bar B the double bar. Otherwise A bar B also available, but here everything bar is there, so that we are using double bar. While double bar is got cancelled, final expression will be A bar B only, right? So the final expression will be A bar B, right? How to implement this A bar B? So this is already available here. A bar B is already available, that is given as a single input, right? The single input means it will act as a NOT gate. So what is the output here? A bar B the whole bar If it acts as a NOT gate, mean again one more bar will be added. A bar B to the whole bar is given as a input. Because of NOT gate, we have one more bar is there. So this double complement got cancelled, so that we have A bar B. So this is the output of the half subtractor borrow, right? So by using this logical circuit will produce the output of difference as well as borrow of the half subtractor. So in this video we discuss about the half subtractor, details about the half subtractor, then how to implement with the NAND gate. While implementing NAND gate, in order to convert into AND operation, we are taking complement 2 times, so that we can easily implement with the NAND gate. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening.